You know, if you spend enough time on AI, Twitter, or X, or whatever we're supposed to be calling it this week,
Right, yeah.
you inevitably run into the insults. There's this whole culture of dunking on the current state of the tech, and there is one insult in particular that really, really sticks. It's kind of the ultimate put down for a large language model.
Stochastic parrots.
Exactly, stochastic parrots.
Yeah.
The whole idea being that these incredibly expensive, massively power-hungry models are basically just, well, fancy birds.
They're mimics.
Right. They can recite Shakespeare, they can write code for you, they can even, like, flirt with you, but they don't actually know what any of it means.
No, they're just predicting the next likely sound.
Yeah.
It's the difference between actually understanding the deep human tragedy of Hamlet and just knowing which words usually follow to be or not to.
Right, the statistical probability of the word be coming next is just really high.
Exactly. And for the last few years, the industry's answer to that parrot problem has been pretty singular. Just make the parrot bigger,
More data, more GPUs.
shovel in more parameters. The thinking was, if the parrot is big enough, maybe it magically turns into a human.
Which is, frankly, a trillion-dollar wager at this point.
It really is.
Yeah.
But what we are unpacking in today's deep dive is a whole stack of new research that basically says no. Bigger isn't the answer, or at least it's not the only answer.
Right.
If we actually want to reach the summit, artificial general intelligence, AGI, we can't just brute force our way up the mountain anymore. We have to establish a base camp.
A base camp, I love that metaphor. It implies we're not actually ready for the summit push yet because our gear is fundamentally broken.
Precisely. The papers we're looking at today, they identified massive structural bottlenecks in how current deep learning works. We're talking about fundamental flaws in reasoning, in how knowledge gets tangled up, efficiency, and self-evolution.
So the argument is that before we scale up, we need to fix the actual architecture.
We need to build a better brain, not just a bigger one.
Okay, so just to set the stage for you listening, this isn't a deep dive about GPT-5 or whatever the next incremental update is. This is about the blueprints for something entirely new.
Completely new paradigms.
We're going to look at 4 specific breakthroughs today. First, there is the hierarchical reasoning model, which is about giving AI an internal monologue. Then cat's net, which separates concepts from pixels.
That one is fascinating.
It's wild. Then we have sequential attention, which is a mathematical fix for how AI focuses. And finally, the Darwin Gödel Machine, which is essentially AI writing its own genetic code.
It's a packed roadmap.
It is. So let's just jump right into the first one, the silent voice, because this connects directly to that parrot problem we were just talking about.
It's the reasoning bottlenecks.
Right, because right now, if I ask ChatGPT a really hard logic puzzle, it usually has to use that chain of thought prompting, right? It has to write out step 1, step 2, step 3.
Out loud, token by token. And that is a huge structural limitation. If you think about how standard transformers work, they are strictly feed-forward. Input comes in, the layers process it, output comes out. It's a straight line.
So it's basically a reflex.
Exactly.
Yeah.
In computer science terms, we say these models are shallow. They are restricted to specific complexity classes. The papers mention AC0 or TC0.
Okay, let's unpack that a bit. Complexity class AC0. Can you translate that for the non-computer scientists tuning in?
Sure. Think of it like this. Imagine you are taking an incredibly difficult math test,
Okay.
but you are forced to shout every single step of your thinking out loud the exact second it pops into your head.
Yeah.
You cannot stop. You can't pause to think silently.
Oh, wow.
And you definitely can't realize you made a mistake in step 1 and go back and fix it in your head before you speak the final answer.
That sounds like a total nightmare. I'd fail immediately.
Right. But that is exactly how a transformer works. It lacks what we call computational depth. It literally cannot mull things over. If the first word it predicts sends it down the wrong logical path,
The train has already left the station.
exactly. It just keeps predicting words based on that bad foundation.
Humans definitely don't work like that. If I'm solving a puzzle, I just sit there. I stare at the wall for a minute. I try a path in my head, hit a dead end, backtrack, and then I finally open my mouth and give you the answer.
And that stare at the wall phase is exactly what the hierarchical reasoning model, or HRM, is trying to replicate. It introduces a multi-timescale architecture.
Multi-timescale, so it has different gears.
You could say that. It separates the internal monologue from the actual output. It allows for latent reasoning.
Latent just meaning hidden, right?
Hidden, exactly. Instead of predicting the next English word, The model performs a tree search in a hidden state space. It simulates different logical paths, evaluates them internally, and only when it finds a high-confidence solution does it actually generate the output token.
So it's actually thinking before it speaks.
Yes. It converts the problem from a simple linear prediction task into a loop-based reasoning task. And the really fascinating part is that this isn't just a clever software trick. The researchers drew direct biological inspiration from the mouse cortex.
Wait, we're modeling cutting-edge AI on mice now.
Brains are brains. Mammalian brains have evolved to solve exactly this efficiency problem. The research highlights this concept of a dimensionality hierarchy.
Okay.
In a biological brain, you have these high-level planning areas. Think of it as the manager part of the brain. These areas operate in a very high-dimensional space. The paper actually quantifies this with a participation ratio of about 89.95.
Okay, so nearly 90, meaning it's juggling a lot of complex, abstract variables all at once.
Exactly. It's highly flexible. It's playing out scenarios. But
Yeah.
then you have the low-level execution module, the part that actually fires the muscle to move the whiskers or generates the specific action. That operates in a much lower dimensional space, around 30.22.
So you have high-level cognitive flexibility paired with low-level execution precision.
Correct. And the HRM architecture mimics this exact split. You have a high-dimensional latent space for the thinking, the mulling over, and a low-dimensional space for the talking.
That makes so much sense.
And the results they got are just wild. They tested this on the ARC AGI challenge.
Oh, I know that one. That's the benchmark that famously breaks all the big LLMs. It's all about novel visual logic patterns. You can't just memorize the answers from scraping the internet.
Right. Most models completely fall apart there. To give you some context, Claude 3.7, which is a massive state-of-the-art model, scored 21.2%.
Ouch.
Yeah. And OpenAI's specialized reasoning model, O3 Mini, scored 34.5%.
Okay, so better, but still failing the test. What did the mouse brain model get?
The HRM scored 40.3%.
Wow.
And here is the kicker. It achieved that using only 1,000 training examples.
You're kidding?
No, a tiny, tiny fraction of the data those giant models use.
That is a massive jump, 40.3% on just 1,000 examples.
It basically proves the point. Computational depth, the ability to think silently and backtrack, is a prerequisite for AGI. You cannot just scale up a shallow circuit and magically expect deep thought. You have to build the loop.
Okay, so if HRM fixes the brain's ability to reason, we still have a huge problem with how these models actually organize the stuff they know. Which brings us to the second breakthrough in our Basecamp roadmap, CASNet.
Yes.
And this one really digs into how AI sees the world.
It deals with what we call the entanglement problem.
Right, which is the issue that in a normal neural network, everything is basically just soup.
It is entirely soup. Say you train a standard neural network to recognize an apple. That concept of an apple isn't stored in some nice, neat labeled folder on a hard drive.
It's everywhere.
It's smeared across millions of weights and parameters. The idea of the apple is hopelessly entangled with the color red, the round shapes, the concept of fruit, and even the background pixels of the images it was trained on.
So if I want to take that isolated apple concept and, say, put it into a completely different robot's brain, I can't.
No, you'd basically have to move the entire brain over. It's incredibly inefficient and rigid. So CATSNet proposes a way to fix this, and strangely enough, their solution goes all the way back to linguistic theory from 1916, Ferdinand de Saussure.
The father of semiotics.
Exactly. He famously distinguished between the signifier, which is the symbol or the word itself, and the signified, which is the actual mental concept behind it.
Okay, so to use the apple example, the word apple is the signifier, but the crunch, the sweet taste, the idea of the fruit in your mind, that's the signified.
Right. And CATSNet builds a dual module architecture to explicitly mimic this separation. It has a concept abstraction module, or CA, and a task-solving module, the TS.
But if they are separate modules, how do they talk to each other?
The concept module looks at the raw sensory data and compresses it down into a very low-dimensional vector. Imagine a simple code, maybe just 20 numbers long. That tiny vector represents the pure concept. It then passes that vector over to the task module to act as a gate.
A gate? You mean like a filter?
Exactly like a filter. It's
Yeah.
a mechanism called hierarchical gating. Think of it like this. Even if there is no actual food in front of you, if I magically activate the dinner concept vector in your brain, it entirely reconfigures your processing.
Oh, I see. I'd suddenly become hyper-aware of plates, the smell of cooking, forks.
You are primed for dinner. The concept dictates how you process reality from that moment on.
The paper actually had a really cool visualization of this. They showed the network an image that contained both a lifeboat and a seashore in the same picture.
Yes, the attention map experiment. This is the proof in the pudding for CatsNet. When the researchers plugged in the lifeboat concept vector, the network's attention map locked strictly onto the boat. It completely ignored the beach.
But the image didn't change.
Image didn't change, weights didn't change. But when they swapped it and plugged in the seashore concept vector, the attention shifted entirely away from the boat and focused solely on the sand and the water.
So the concept vector is quite literally like putting on a pair of glasses that highlights very specific parts of the world.
And because that concept is decoupled from the main processing weights, because it's just this tiny, highly portable 20-dimensional vector,
Yeah.
you can do something that feels straight out of science fiction. You can beam thoughts between machines.
Yes. The teacher-student experiment, I have to admit, when I read this part of the paper, I actually had to put it down and just stare at the wall for a second myself.
It's remarkable.
Yeah.
Okay, so they took a teacher network that was fully trained and knew 100 different categories of images. This is using the CFAR 100 data set.
Right.
And they had a student network that only knew 99 of them. The student had never seen an apple. It was totally computationally ignorant of the concept.
And normally, to fix that ignorance, you would have to show the student network thousands of pictures of apples and run heavy compute to retrain it for hours.
Right, massive gradient updates. But instead, they had the teacher simply transmit the concept vector for apple through a lightweight translation module. No gradient updates on the main network. No training in the traditional sense at all.
It just downloaded the concept, like plugging in a USB drive?
Exactly. And instantly, the student network could identify apples in new images with a mean accuracy of 0.7292.
Over 72% accuracy without ever seeing one. That is literally the I know Kung Fu scene from The Matrix.
It really is. The authors call it learning by communication. Think about what this means for robotics. We don't need massive joint retraining for entire fleets of autonomous agents anymore. One robot encounters a new hazard, say, a slippery floor. It distills that hazard into a low-dimensional concept vector and just beams it to the rest of the fleet instantly.
And they all just get it. They all know what a slippery floor is without having to slip themselves.
Exactly. And the researchers even noted that this decoupling aligns with human biology.
Wait, really? Where?
In the ventral occipitotemporal cortex, or VOTC, that's the part of our brain that handles semantic control. We store concepts as low-dimensional triggers to modulate our visual processing, just like CatsNet does. So once again, fixing the architecture means moving closer to biology.
Okay, so mapping out our base camp so far. We have a brain that can reason silently with HRM. We have a brain that can decouple and share pure concepts with CatsNet. But we still have to run this thing efficiently in the real world.
Right.
If we want AGI, we can't have it burning the output of a nuclear power plant every time it needs to look at a picture.
This is the feature selection problem, finding the needle in the haystack. And this brings us to the third breakthrough, sequential attention.
Now, attention is obviously the buzzword of the AI decade. Attention is all you need is the title of the famous paper that gave us Transformers in the first place, so why do we need a new version of it?
Because standard attention, as revolutionary as it was, is actually quite naive in how it selects information.
How so?
It looks at features in isolation. It essentially asks, is this specific bit of data important? And it asks that question regarding every single bit independently.
Which seems fine logically, until you realize just how much redundancy there is in the real world.
Exactly. I like using a packing analogy to explain this. Imagine you're packing a very small travel kit for a weekend trip. You have highly limited space, a strict budget.
Okay.
Standard attention looks at a toothbrush on the counter and says, this is vital for hygiene. I will pack it.
Good decision.
Then it looks at a second toothbrush. It evaluates it in total isolation and says, this object is also vital for hygiene. I will pack it. Then it sees a third toothbrush, vital for hygiene, pack it.
So you end up with a travel bag full of 10 toothbrushes and absolutely no socks.
Precisely. Standard attention completely ignores residual value.
Residual value, meaning the value of a feature given what you already have in the bag.
Right. It packs highly redundant features because they all look individually important if you don't consider the context of what you've already selected.
Okay, so how does sequential attention actually fix the toothbrush problem?
It uses an algorithm based on greedy forward selection. Instead of picking everything at once, it selects features one by one over a set number of rounds. It picks the most important feature first. So toothbrush number one goes in the bag.
Makes sense.
But then And this is the crucial algorithmic shift. It updates its context. Before it picks the second item, it looks at the remaining features and asks, what adds the most net new information relative to the toothbrush I already have?
So it looks at the second toothbrush, checks the bag, and goes, nope, dental hygiene is already covered. What's next? Ah, socks.
Exactly. It built a diverse portfolio of features rather than a redundant pile. And the mathematical backing for this is really strong. The paper by Yasuda and colleagues proves that for linear regression, this sequential attention method is mathematically equivalent to orthogonal matching pursuit, or OMP.
But they adapted it for deep neural networks using a one-pass implementation, right?
Yes, which makes it computationally feasible at scale.
Hmm.
They tested this on the Criteo dataset, which is an absolute monster, 3 billion examples.
Wow.
And sequential attention significantly outperformed traditional feature selection methods like lasso, especially when they needed to select more than 15 features.
There was a visual in the paper with the MNIST dataset, the handwritten numbers, that really clarified this for me.
Oh, the pixel selection visual, yes.
Yeah, if you look at how standard methods choose which pixels to pay attention to, they pick pixels scattered randomly all over the image to try and figure out if it's looking at a 3 or an 8.
It's just noise.
But sequential attention picked a highly focused clump of pixels that actually defined the specific curve of the number. It fundamentally understood that pixels right next to each other provide redundant context, so it only needed a few in the right spot.
It is strictly more efficient. It learns to ignore the noise and the redundancy. And for an AGI operating in the real world, efficiency isn't just a nice-to-have. An agent can't process every single photon hitting his camera. It has to know exactly what to ignore.
All right, so we've built an incredibly sophisticated machine here. HRM gives it deep reasoning. CatNet gives it portable concepts. Sequential attention makes it ruthless about efficiency.
It's a solid base camp.
It is. But our roadmap has one final pillar. And this one honestly feels like the most sci-fi, or maybe the most dangerous part of the whole thing, depending on how you look at it.
You're talking about the engine for self-improvement.
Right. The Darwin Gödel Machine, or DGM. This is trying to answer the ultimate question. How does the AI get better without humans having to constantly tweak it?
This is the holy grail of open-ended self-referential evolution. Because right now, if a model hallucinates or makes a logic error, a human engineer literally has to go in, adjust the training data, or tweak the hyperparameters and run it again.
It's manual labor.
It's tedious. DGM proposes a system where the AI functions as its own coding agent. It doesn't just adjust a few internal weights, it actually rewrites its own underlying Python source code.
It is quite literally editing its own brain.
It's editing its own fundamental logic structures. But what makes DGM unique is how it decides which edits are actually good. Unlike a human programmer who relies on formal logic or proofs, DGM uses Darwinian selection.
Survival of the fittest code?
Exactly. The system generates mutations of its code, just little random changes or new programmatic ideas. Then it tests those mutations against rigorous benchmarks like SWE bench.
And if the performance improves?
If it improves, that mutation survives and becomes the new baseline code for the next generation. If the mutation breaks the system or lowers the score, it dies. It's an engine for open-ended evolution.
That sounds incredibly powerful, but it also begs a massive question. How do you stop it from just drifting into complete nonsense if it's just blindly mutating? Couldn't it eventually optimize for the wrong thing entirely?
That is the primary risk of self-evolving systems, reward hacking. And that's exactly why the Basecamp roadmap pairs DGM with something called neurosymbolic grounding, specifically a framework called GraphMERT.
GraphMERT, that sounds like a Muppet. What exactly does GraphMERT do?
It acts as the anchor. It distills unstructured data into rigid knowledge graphs. It basically forces the evolving AI to ground its reasoning in verified, factual relationships, ensuring provenance before it's allowed to evolve.
Oh, I see. It's like giving the AI a strict fact checker that sits on its shoulder while it mutates its code.
Exactly. It ensures that the evolutionary jumps are tethered to factual reality, preventing runaway hallucinations.
Yeah.
And there's one final critical piece to this adaptability strategy. Protein TTT.
TTT stands for test time training, right? Or test time adaptation.
Yes. This solves the outlier problem. Usually, once a neural network finishes training, its weights are frozen.
Right. It is what it is.
So if it encounters something completely weird out in the real world, an extreme outlier,
Yeah.
it just fails.
Like a self-driving car encountering a person in a dinosaur suit riding a unicycle. It wasn't in the training set, so the car just panics.
Exactly. Protein TTT changes that. It allows the model to continuously customize its internal representations on the fly, just for that single anomalous sample. It does this by minimizing complexity in real time.
So it is actively learning during the test itself.
It adapts to the specific weirdness of the moment, figures out how to handle the outlier, and then it can reset. It gives the system the dynamic flexibility it needs to handle the unexpected, which, let's face it, is the definition of operating in the real world.
Okay, we have covered a massive amount of ground here. Let's try to pull all of this together for the listener. We started with the insult that current AI is just a stochastic parrot.
A very big, very expensive parrot.
But we've arrived at a blueprint that looks absolutely nothing like a parrot.
No, it doesn't.
It really is a base camp for AGI. Let's just look at the synergy of these four breakthroughs. You have HRM providing the computational depth to actually reason and backtrack silently, which fixes the logic bottleneck.
Right.
You have CATSNet separating out concepts so they can be instantly shared and transferred, which fixes the knowledge entanglement bottleneck.
Yep.
You have sequential attention filtering the world so the AI focuses only on what adds net new value, fixing the efficiency bottleneck. And finally, you have DGM and protein TTT, which allow the system to rewrite its own code, evolve, and adapt to wild outliers in real time.
When you lay it all out like that, it sounds significantly less like a chatbot predicting words and much more like, well, an organism.
An organism, that's exactly what I was thinking. We are moving away from brute force statistics and massive data centers and moving toward bio-inspired architecture.
That is the core takeaway from this entire research stack. To get to actual AGI, we don't need to just stack up more GPUs. We need to build a fundamentally better architecture. We are trying to engineer a brain, not just a really good predictor.
It really does make you rethink the entire trajectory of this technology. It's not just about the models getting bigger anymore. It's about them getting deeper.
It's the evolution of a new species of software.
You know, there's one provocative thought I just can't shake from all this. Going back to the CNET experiment, the idea of beaming those concept vectors between the teacher and the student.
The machine language implication.
Yeah. If these machines can actually compress a complex, nuanced reality concepts like dinner or justice or a slippery floor into a tiny 20-dimensional mathematical vector and just instantly beam it to one another without training.
You're realizing they really don't need us to talk to each other.
Exactly. We communicate using these clunky sound waves and type English words. It's so slow, it's incredibly lossy. But if they are trading pure, high-dimensional concept vectors natively,
then we are quite potentially witnessing the birth of a true machine native language, a communication system that is exponentially faster, denser, and far more precise than English or Python could ever be.
and it's a language that we as humans might not even be able to read or comprehend.
It would be a secret high-speed handshake between neural networks. It is a deeply provocative thought. If they develop their own hyper-efficient shorthand for reality, will we still be the ones guiding the conversation? Or will we eventually just be the ones providing the electricity to keep the servers on?
Well, that is a terrifyingly wonderful place to leave it today. I am going to go think about my own concept vectors and try really hard not to spiral.
Don't hurt yourself.
Thanks for taking this deep dive with us today. We'll catch you next time.